based surface analysis. Now, as you know that continuous fields are not the same as discrete fields. They have certain characteristics which are not the same or not shared by discrete fields. They keep changing continuously. So here we need to consider certain things like what is the slope angle, what is the slope aspect, what is the concavity or convexity of the slope, not just where is the slope. So these notions are maybe not applicable to discrete fields, but they are applicable to the continuous fields. So we regularly refer to continuous field representation as DEM. What is DEM? DEM stands for Digital Elevation Model. It is a 3D graphical representation of a terrain's surface, of the surface of a terrain. Now let's go to applications. There are numerous examples where more advanced computations on continuous field representations are needed. So we will try to find out these calculations. The first one is slope angle calculation. It calculates the steepness of the slope. What is the angle at which the slope is getting formed? So this slope can be determined either in degrees or percentages. So suppose there is one point here and there is another point here, then the slope is in this direction and there is an angle at which this slope is getting formed. So what is this angle? Okay, so that is the slope angle. The next thing is the slope aspect calculation. Slope aspect means in which direction is the slope getting formed. Is it going upwards? Is it going downwards? What is the slope? Where is the slope facing? So that is the orientation of the slope in degrees. So that's why it can go from 0 degrees to 360 degrees. That means it can go from 0 degrees when you go up and can go around up to 360 degrees. So this is how you can have a slope aspect. I'll just give you an example. Say how is the slope aspect calculated? From 0 degrees to 22.5 degrees is considered as north, and from 22.5 degrees to 67.5 degrees is considered as northeast, and so on. Say 67.5 degrees to 112.5 degrees is considered as east. And so on. So this is how the aspect of the slope is calculated. The next thing is slope convexity or concavity. So what do you mean by slope convexity or concavity? It is the change of the slope. How is the slope changing? If this change in the slope is negative, then it is a concave slope. That means it is going from a higher value to a lower value, then it is a concave slope. Whereas if the change is positive, that means it is going from a lower value to a higher value, then it is a convex slope. So this is a concave slope. And this is a convex slope. I hope you understand that. Next thing is hill shading. Hill shading is used for hilly or mountainous areas. It is used to show or depict the difference in the relief or the surface and the terrain morphology. That means how the slope is changing in different hilly areas. In hill shading, different color tones are given to the raster to represent the amount of light which is reflected by each location depending on how it is oriented towards the light source. So usually the illumination source is chosen at an angle of 45 degrees above the horizon in the northwest direction. Slope length calculation. Now what is a slope length? Let us consider that this is the slope. So if you draw a vertical from here and a horizontal from here, okay, so this horizontal is called as a run and this vertical is called as the rise, and this is your slope length. So the slope length can be found by using the Pythagoras theorem. That is, the slope length square is equal to the run square plus the rise square. Three-dimensional map display. You can create some three-dimensional views of the digital elevation model. You can show the location of the viewer, the angle under which he or she is looking, the zoom angle, and the amplification factor of the relief. That means what is the location of the viewer, what is the angle under which he or she is looking. Many factors can be shown. How is the three-dimensional view constructed? You can have a predefined mesh which can be put over the DEM, or you might be having some satellite image which is draped over the DEM, or you can also use some kind of raster like the hill shading raster which I have just explained. Next thing is the determination of change in elevation through time. So suppose there is a dig which has to be filled up, or you want to level the ground, then how much leveling is required? The cut and fill volume of the soil, either if you want to remove it, then the soil to be removed, or if you want to fill in the soil, then how much volume of soil do you want to bring in to make the site ready for construction. Okay, this is what you want to compute. So it can be computed by overlaying the DEM of the site before the work begins and overlay with the DEM of the expected topography of the site. That means what is the DEM of the site before the work begins. Compare it with the DEM of the site, what you're expecting after the work has been finished. So you can also find out what will happen if there is a landslide. So you can determine landslide effects by comparing the DEMs of before and after the landslide event has occurred. Catchment boundaries or drainage lines can be automatically generated if you have a good quality DEM, and we can use some neighborhood functions for that. So let's see how automatic catchment delineation can be performed. First of all, the system will determine the lowest point in the DEM because that will be considered as the outlet of the catchment. Starting from that lowest point, it will repeatedly keep searching the neighboring pixels with highest altitude and go on going to the highest altitude. In this process, it will reach to that point where the boundary can be formed. This process is continued until the highest location is found, and the path followed determines the catchment boundary. Whereas if you are trying to find out the drainage network, if you're trying to delineate the drainage network, the process is reversed. Now you will start working from the watershed and you will go downwards. Each time you are looking for the neighboring pixel with a lower altitude. This will determine the direction of water flow. Dynamic modeling. Dynamic modeling is used to find out the effects of certain events. So, such as computation of surface runoff or erosion. Now, how is the soil going to get eroded? Or what will be the flow of the groundwater? Or what will be the areas affected by the pollution? So, what is the delineation of those areas? What are the boundaries of those areas? Then, what will be the areas covered by processes such as if the lava starts flowing, then how much area will be covered dynamically, and slowly the area that will be covered by the lava or by the debris. Next is visibility analysis. Visibility analysis, as you can understand, it is about how much area is visible or what is visible from a particular location. So a view shed is the area that can be seen, that is that area which is in the direct line of sight from a specific target location. So if you're standing at a particular target location, what is the area which is in sight of you? That is called as a view shed. So visibility analysis determines the area visible from a scenic lookout. It is the area that can be reached by a radar antenna also. That means from which area it can catch the signals, or it can assess how effectively a quarry or a road will be hidden from view. So if it is a hilly area, then maybe from one location a road may not be visible. Filtering. Now the process of filtering is similar to the moving window averaging, which we had seen earlier. Here too we define a window, and we are going to move this window over our input raster one cell at a time. So for each cell, the system is going to perform some computation using that window, and whatever result it is obtaining from after that computation, it is going to assign it to the output raster. That means you have an input raster, you use a filtering window over that input raster, that means your input data. After the computation is performed, you get the result. You move that result to your output raster. Then you move the window to the next cell. So here the moving window is filtering the input raster, and this moving window is actually itself a little raster. It will be having its own values which will act like the input filter. So here we are having in figure A, here we are having an filtering raster which is forming the window for filtering. This raster is called as a kernel. It is a 3x3 raster. The values which are mentioned in this raster are used for filtering, and these are the weight factors. So if you consider the figure A, you can see that all the values are equal to 1. So there are 9 cells in this since it is a 3x3 raster, and each one of them have been given the equal weight. in the computation of the filtering step. So whatever be the input raster values, they will be given equal weightage if they pass through these 9 cells. If you look at figure B, the weights are different, and similarly the figure C, here the filtering has different weights. Now let us assume that the input raster is denoted by Rij. So input raster cell values are Rij. I stands for the row and J stands for the column, and the corresponding filter values are given by Wij. So the input values are Rij, whereas the filter values are Wij. Now what will be the output value for each cell under consideration? So here you can see there is a formula given which says that summation Ij of Wij multiplied by Rij will be divided by the summation of all Wij's. So in this case, the output value for any cell under consideration will be computed as the sum of the weighted inputs divided by the sum of the weights. So if you are considering any cell, then what is the weighted sum? That means Wij multiplied by Rij divided by the sum of the weights.